Check it out now, y'all.
NanoHub U, online instruction.
In this lecture, we'd like to describe some of the important results that that come from a model for electron states and solids called a nearly free electron model. And this nearly free electron model attempts to address the issue of this constant electrostatic potential energy that's characteristic of the free electron model. And so in particular, what we like to do is we like to slowly turn on the interaction potential energy between electrons and the nuclei in the atoms that comprise the solid. And so everywhere there's an atom core now, we like to introduce a modulation in the bottom of this potential well. This modulation is going to be modeled in a nearly free electron model by a sinusoidal wave, and the amplitude of that, the peak-to-peak amplitude of that sinusoidal wave is going to be given by this parameter 2 times u sub 1, and we'll try to explain that in what follows. And in particular, we're kind of really interested in what happens to the wave functions when you introduce this modulation, which is periodic in the lattice of the crystal. And we'll find out that some very interesting new results come about. So to describe the model in detail, when x is between 0 and L, right? So L is going to be the length of our crystal. We're going to let the bottom of the potential well just be given by this U1 cosine of G1x. So G1 is our reciprocal lattice vector, and this just means that the potential in a nearly free electron model, the electrostatic potential energy is modeled as a cosine 2 pi a over x, where again G1 is our reciprocal lattice vector. Now, this model for U of x guarantees that the electrostatic potential energy is periodic under displacements by the lattice constant A of the metal. But the modulation in the electrostatic potential energy is rather well defined. It doesn't have this very sharp discontinuity associated with the atom cores that we've described in the previous lectures. That can be fixed up. That's a detail, but it's worthwhile to understand the consequences of this model in some detail. So let's follow that through. We're going to start by assuming that there are free electrons that have wave functions given by e to the ikx that move in this potential well with this sinusoidal modulation to the bottom. We'll recall that in general there's going to be a free electron wave traveling to the right. That's going to be given by a plus e to the ikx, where the argument is associated with a positive sign. A wave traveling to the left would be an e to the minus ikx. We're going to subscript each wave function by its quantum number k. So again, for electron states and metals, the individual quantum numbers are all contained in the wave vector k. And if we specify k, that's basically telling us what quantum state we're in. And the other thing we have to recall is that from before, k is going to be an integer multiple times 2 pi over L, where L is the length of the crystal. So since the length of the crystal contains n atoms, this quantity L is going to give k value. This quantity L is going to be quite large, right? It's going to be on the order of centimeters when we evaluate the increments between the various values of k. That just simply means that the separation between the different values of k is going to be very small because this very large number L appears in the denominator. The interesting new thing that's possible now is that these quantum states that are described by these plane waves, right, they could be reflected from the potential energy, the modulation in the potential energy introduced by the core atomic states in the solid. So let me remind you of something that we discussed way back at the beginning of the course. We considered the case when a particle of mass m had an energy E and was described by a plane wave that was traveling to the right. And when that plane wave state encountered a potential barrier, and in this model, the potential barrier was modeled as a sharp, abrupt, square potential barrier of height u naught, something very interesting happened. Some of that wave was reflected with an amplitude b, and that was given the wave function e to the minus k1x, because now it's traveling in the opposite direction. And some of this wave function could be transmitted over the barrier, and the transmitted wave function was given this wave function c, e to the I k2x, over this region where the barrier is located. So this is a purely quantum phenomenon, right? If this particle were a classical particle, and if its energy E was greater than U0, then that particle would transmit across the barrier with unity probability. It would always make it over the barrier. But in quantum mechanics, these changes, these abrupt changes in the potential energy cause reflections, and that's just a quantum phenomenon, right? So the question simply becomes, is it possible that when we modulate the interaction potential energy by this sinusoidal function, is it possible that we could start to acquire a reflected electron state at the location of each of these atoms in this one-dimensional crystal? And the answer to that question has to be worked out, and you have to understand what the consequences of that possibility are, and that's what we discuss in the next slide here. Here we sort of simplify the case. These are the atom cores. They're spaced periodically by a distance a, and we're going to just say that this wave function moving from left to right has a certain probability of being reflected at each location where this atom is located. And that reflected electron wave is going to be represented by the red wave function here, psi of minus k. And what we're asking is it possible that this blue state is totally reflected to form the red state? What are the conditions for this fully reflected interference to occur? And that fully reflected wave would develop if a special condition is satisfied, and it's not surprising what that condition is. That condition would say that an integer number of wavelengths of this electron state is just equal to the path difference between, let's say, the blue wave and the red wave, right? So the path difference between the blue wave would be down, and then it would be reflected back. So that path difference in this model, this very simple model, would be 2a. And so the point is that if there's some reflection that occurs at each atom, and if there's a large number of atoms, it's possible that you could get a reflected wave that actually prevents the propagation of this wave along the positive x direction. And the condition for that to occur would be this relationship between wavelength lambda and the periodicity of the lattice A. So this gives us a condition for wavelengths L for this quantum state, for this fully reflected wave to develop. So it's a model, right? It's a model. Once we know the wavelength that this fully reflected wave is going to develop, then we want to calculate immediately what the allowed, or what the k vector would be for that particular electron state. And the k vector for that particular electron state would just be 2 pi over that magic value for lambda. Here we substitute in the expression for lambda that we wrote down on the previous slide. And what we find is that if this fully developed wave is possible, it's going to happen at a k vector which is given by an integer n times the reciprocal lattice vector g1 divided by 2. Okay? So this reciprocal lattice vector that we defined about 3 or 4 lectures ago has a way of constantly reappearing in this discussion of electron states in periodic solids. And here what we're saying is that if k is equal to, let's say, half integer multiple of g1, then it's possible that an electron state that tries to move through the lattice would be totally reflected. And that's just basically saying that the wave will not propagate, right? It can't make it through the lattice. It's totally reflected by the modulation in the electrostatic potential energy of the lattice. So, in principle, we would have to consider all possible values of n. And what follows, we're just going to choose n equals 1 to make the arithmetic simple, and hopefully the arguments will be understandable. We're also going to focus on one dimension. That alleviates a lot of the vector algebra that's required to discuss this possibility in 3 dimensions. If the incident wave traveling from left to right is designated by this wave function psi of k, and if the reflected wave that's traveling from right to left is designated by this wave function psi of minus k, then the total wave that sets up in this lattice would then just be the sum of these 2 waves, right? And if the incident wave is completely reflected, then the coefficients a and b that we used in the previous slides of this lecture, those 2 coefficients would be equal, and they would be equal to some parameter p. And that just simply means that we can now write down 2 possible wave functions that describe this reflected wave interfering with the incident wave in the metal. Not surprisingly, these are going to be standing waves, because anytime you've got a wave moving to the right, e to the ikx, another wave, e to the minus ikx, moving to the left, when you add those 2 waves up together, hopefully you all appreciate from our discussion early on the first week of the semester, that gives rise to a standing wave. So you can use Euler's formula to realize that if the reflected wave is in phase with the incident wave, then there's going to be a positive sign here. So this is the reflected wave, this is the incident wave. Positive sign is just telling you they're reflected in phase. That gives rise to an even wave function that's no longer imaginary. It involves cosine of kx, where k is now has to be evaluated at the reciprocal lattice vector g by 2. The other possibility is that the wave could be reflected out of phase with respect to the incident wave. That gives rise to a negative sign here. And again, by Euler's formula, this now gives rise to an imaginary wave function which can be described as the sine of kx, where again, k has got to be evaluated at the reciprocal lattice vector divided by 2, g1 by 2. Okay? So, we have the interesting result that if this reflection can set up, we have standing waves. Both waves are possible for the same value of k, right? One is it requires a cosine function, the other requires a sine function. And these 2 waves are designated as even and odd to represent the fact that the cosine and the sine have different symmetries about x equal to 0. Now, you can say, well, so what? That's interesting, but so what? Well, the so what comes about when you plot the wave function times its complex conjugate is a function of x. And what you find is that for the even wave function, right, the probability density of that electron state is actually lined up with the atoms in the crystal. So the negative electrons that are described by the wave function psi even lie actually, they're localized and they lie on top of the atom cores, which are positive. And schematically, I've tried to indicate that alignment in this diagram. It's interesting to contrast that to what happens when you take psi star psi for the odd wave function. Then you end up with a sine squared dependence, and that sine squared dependence actually shifts the electronic charge midway between the two positive ion cores. So the difference in these two wave functions just is a shift in the alignment of the the electron charge distribution with respect to the positive lattice. So because the wave function, or because the wave vector k is the same for both these waves, right? The wave vector k is g by 2, right? The kinetic energy, which is given by h bar squared k squared over 2m, that's going to be the same for both waves, right? There's no difference because the k value is the same for both situations. The difference occurs in the electrostatic potential energy that develops because of these two different alignments of charge, right? And that requires us to do a simple calculation. The first step in the calculation is to find out what the value for P is, right? So we have to go through this normalization integral, and here I show that P is equal to 1 over square root of 2L for this simple one-dimensional model. The potential energy is now a little bit more complicated. We have to find out what the expectation value is for the potential energy for the even wave functions and the odd wave functions when k is precisely equal to g1 by 2. And so we have to go back to our understanding of quantum mechanics. We have to evaluate the expectation value of u of x, where now u of x is just given by this nearly free electron model that takes the interaction potential energy and represents it as a single sinusoidal wave with a periodicity of g1 and an amplitude of u1. And so we have to now evaluate this integral for psi even, psi star even. We also have to repeat the expression for, or we have to repeat the calculation for the odd expectation value for the potential energy. So, you know, I worked through the arithmetic. You can check my algebra at home. But what you find is you find the expectation value for the potential energy for the even wave functions turns out to be equal to u1 by 2. And similarly, you can do the same calculation for the odd wave functions. You just have to replace cosine squared here by sine squared, so the integrals are a little different. But when you do that valuation, you find out that the expectation value for the potential energy for the odd wave functions is minus u1 by 2. And this just simply means that the even situation, this alignment of charge with respect to the atom cores, has a slightly higher electrostatic potential energy than this configuration, where the electron states are aligned midway between the atom cores. There's good reasons for that. You can develop simple models, right? Because if you pile up a negative charge between two positive ions, that negative charge will reduce the Coulomb repulsion between these two positive ions. So that'll tend to lower the electrostatic potential energy. And this situation is just the opposite. So that slightly raises the electrostatic potential energy. The question is, how much is it raised? How much is it lowered? Well, on the basis of our simple model, right, the difference the difference between the expectation values for the even and the odd potential energies is just going to be given by this expression U1, where U1 is just the amplitude of the Fourier coefficient in U of x that we put into the problem up front, right at the beginning. So it's a very simple, very nice result. It's somewhat intuitive if you just consider this possibility that the electron states can be reflected, and if the reflection occurs at a particular wavelength, it'll constructively interfere with the incident electron states that's trying to propagate through this lattice, and the net result is a standing wave which no longer moves through the lattice, but which is locked, right? It's locked in phase with the atom cores. So that's the nearly free electron model in a nutshell. What it basically predicts is it basically predicts at these particular values of k, which are given by half integer of a reciprocal lattice vector, you'll get a standing wave. And it also predicts that the difference in the electrostatic potential energy between a standing wave described by an even wave function and a standing wave described by an odd wave function, the difference in the electrostatic potential energy of those two quantities is just this parameter U1, which is what we use to model the electrostatic potential energy in a nearly free electron model. So we might expect something very interesting to happen at these particular values of k, which are given as plus minus g1 by 2, where g1 is the reciprocal lattice vector in one dimension. Now, this whole argument has been done for a one-dimensional case, but clearly in 3 dimensions, right, we have ky and kz that we have to take into account. So in 3 dimensions, we would have to use a more transparent vector notation. The arithmetic gets a little bit more complicated, but the same results come out, right? The same key results come out. In certain directions in k space, these electron states that are try to propagate through the metal, those states are turned into standing wave states by this interference with reflected waves from the atom cores. So that's the essence of the nearly free electron model. In the next lecture, we're going to try to describe the consequences of this very simple prediction, and we'll find out that this model actually predicts some things that are experimentally observed, and so that provides some confidence that the underlying assumptions of the model are essentially correct. So the next lecture we'll discuss the consequences of this rather interesting prediction. Thank you.